me. I hope you can hear me and also see the slides well. So yeah, I'll be telling about my research. So it's on a multi-fidelity ensemble Kalman filter, where I use a machine learning circuit model. And I'm a PhD at TU Delft, and my promoters are Martin and Hanne here. And I also presented this last year on the ISDA in Japan. So already you've seen, so the first talk was also like machine learning circuits, and there have been many for, well, specifically here I mentioned some for numerical weather prediction. So you have the Pangu weather forecast.net, GraphCast.net, AIFS. So for example, in the Pangu weather paper, they showed that it had like excellent tracking here of the typhoon. You can see the ground truth in black, and then in blue they have the high-res forecast, and then in red they had the Pangu weather forecast. So it seems to track it here very well. And then later there followed a review about this. If you then look at, for example, wind speeds prediction, then there was here one review where they said that, well, okay, the tracking is nice, but then, for example, the vertical velocity here is underestimated by the machine learning models. So it seems that in some cases, machine learning circuits are not perfect, and high resolution models are better. But of course, we know that usually machine learning models are way faster. And in my research, I try to sort of combine the advantages of both approaches. So the main idea is that this cheap machine learning circuit, we in an ensemble framework, we generate many of those runs from the machine learning model. And then I combine this with a few of the expensive but more accurate high resolution runs. And I do this by using a multi-fidelity ensemble Kalman filter. So that's what I will talk about. So I will briefly say something about multi-fidelity and how you can construct multi-fidelity estimators. Then I'll talk about multi-fidelity eNKF, and I will show a test example with the quasi-geostrophic model. So I will denote multi-fidelity estimator by Z. So how do we construct it? So we start with our initial random variable, which, well, from a control variate perspective, this is the principal variate. And this one is very expensive. And what we then do is that we add a correction to X using a control variable, which we denote by U hat. And this U hat, so well, this will be generated in the end by the machine learning model. But this U hat should be highly correlated with X. So it should say something about how X behaves. So your machine learning circuit should be sort of reasonable enough approximation of the high resolution model. And in general, you then subtract exactly the mean of this U hat. In practice, the exact mean is not known. So then the final step for multi-fidelity estimators is that we also replace this mu of U hat by a third variable, which we then use to get a more accurate representation of this mean. And then in the end, we get here the multi-fidelity estimator that was set, but then we're usually interested in the mean. So the mean here, we take the mean of the first ones, which are generated from your high fidelity model, which is the high resolution model. And then we add this correction term. And also hopefully, so here in the second step, right? So here in step 2, we make an unbiased estimator. So then hopefully here, this one will also be unbiased. And then I use the U hat here from a low fidelity model, which can be either low resolution or maybe a reduced order model, or in my case, a machine learning model. And also I generate U's from the same low fidelity model, but then these U's without the hats, I will generate a lot of those and only a few of the U-hats. So the U-hats I will mostly use to calculate the cross covariances between X and U-hat. And then the U will be used to correct for this mean and take into account the difference of the different ensemble sizes. So there's as a visual representation in an ENKF framework. I took this from the paper and then changed it a bit to match my notation. So of course we have a forecast and an analysis step. And basically what we do in this multi-fidelity ENKF is that we have 3 ensembles at the same time. In the red we have the ensembles that always use the high resolution model. And then in the blue we have the ones that use the machine learning model. So here we take 2 high resolution runs and we take 15, I think, low resolution or machine learning ensembles here. And then we forecast all of them. And then we combine in the analysis step with the same Kalman gain, where the Kalman gain uses the information from all 3 to update to the 3 analysis ensembles. And then we combine those 3 to form this Z variable, and then we can calculate the mean by using the means of each of the individual ensembles. So in the forecast step, we know from ENKF that this is just your standard forecast, and then multi-fidelity ENKF, I add 2 more forecast steps for the U-hat and the U, which both use the machine learning model, which I denote with MU is the cheap model and M of X is the expensive model. And also for later, so N of X will denote the number of high resolution runs, and N of U will denote the number of surrogate or machine learning runs here. And the analysis step is given by this equation for the ENKF, but we can also repeat this one for the machine learning model, so for the control variate and the ancillary variate. And where I have a Kalman gain matrix based on this variable Z. So the Kalman gain will be based on the cross covariances and the covariances of within each ensemble. And then Y is the observation operator, or sorry, observation, H is observation operator. And then, well, there's different ways that you can then tune the different observation perturbation terms. And also instead of observation perturbations, you can also use deterministic ENKF, for example, if you don't want to do this tuning. So then we have here the 3 analysis ensembles. And then the total analysis we can calculate through this formula by applying again this correction to the X by subtracting lambda times this correction term. And this total analysis ensemble, you can calculate then the mean by using the mean of each ensemble. And also here we can calculate its covariance still by using the covariance of each of the ensembles. And then we take the cross covariance for the X and the U-hat because these have the same ensemble size, so we can take cross covariances. And so then we get the full covariance matrix for or improved ensemble and hopefully also an improved estimate compared to X. Then there's some earlier approaches, so this is just as an overview. So if you later want to see some other work that has been done, I won't go through all of them. But there's, you can imagine this main idea. So there's different ways how you can combine an accurate ensemble that's expensive with a cheap ensemble that's less accurate. So there have been different approaches here where they use low resolution models. The multi-level ENKF, for example, so multi-fidelity is a sort of generalization of that, where you have this lambda parameter, but in multi-level, that parameter is always 1. You can do it with reduced order models or autoencoders. Another approach is that you just recenter your high resolution ensemble or your machine learning ensemble with the high resolution information. And also recently the super resolution eNKF. All right, so that's how the algorithm works. Then I will go to the test case. So I've tested this multi-fidelity eNKF on Lorenz 2005, which I won't talk about today, but today I'll talk about the quasi-geostrophic model. So this model describes the stream function and potential vorticity in some rectangular domain for the ocean. And I use the standard equations from the standard test case. So we have the potential vorticity, the Jacobi operator. So we use this beta plane approximation, so we get the Corelli gradient. We have some wind forcing term, and we have then horizontal and biharmonic friction terms. And our state variable will be the stream function. And I use the implementation in PyTorch, which is very nice and very fast, and you can more easily combine that with machine learning. There's also some implementations in Fortran still, but I found this one easier to use. And this implementation is a 2-layer QG model, but then I set the second layer to have infinite depth, and then you get basically the same situation as the equations here. So this is then a snapshot of the true stream function for a chosen set of the parameters. And typically here you see that there's like on the west there's like more activity, and then on the east there's less going on. Typical of these cases. Then I create a machine learning surrogate, and I use a UNet architecture, which you can see here. So it's not the latest of the latest, but the UNet suffices for this case. And then I generate 20 years of training data and 2 years of test data from this model, starting from different initial conditions. And for the observations, so I assume we have some sort of satellite tracks going across the domain at about 300 points. I add some noise with noise level 2, and we make an observation every day, and the model itself has a time stepping of 6 hours. So we have analysis every 4 time steps, and my domain size is 128 by 128. And as eNKF algorithm, I choose here deterministic eNKF, because there's quite a few different ways how you can choose the perturbations for every of the 3 ensembles. So to avoid having to tune that, I choose here deterministic eNKF. And then I choose the lambda equal to 1/2, and there's localization and inflation included also. Then to the results. So this is here the performance for different number of high resolution runs and different number of machine learning runs. And well, for now, still the whites gave me unstable results, so that's why it's white here. But you can see that in general, you get, as expected, well, the lowest error if you have many machine learning runs, and also the highest number of high resolution runs. And also you see that it gets more stable in general, the more machine learning runs that you add. And perhaps more interesting, how does that then compare to eNKF for a different number of high resolution runs? So here you can see with the black dotted line, you see an eNKF if I would have an ensemble size of 100. And I compare that to my multi-fidelity eNKF, where NU is then the different number of machine learning runs. So you can see here that, well, first of all, that it's more machine learning runs gets the RMSE down, but also for a fixed number of high resolution runs, let's say 50, and then I take 20 machine learning runs, gets me already quite close to the performance of eNKF with 100 full runs. So that's the main advantage, is that you can get away with less of these high resolution runs. So that in the end it's cheaper, but still we can get similar accuracy in the end. And what's then important to quantify this is that we have to assume some computational budget. And in my test case, because I used a QG model in PyTorch, so it was already quite fast. So in my case, it's only about 2 times faster. But well, I expect for 3D models, more realistic models, that usually machine learning model speeds up by a lot. So I make here an assumption that, let's say, the machine learning is 10 times faster, and that I can afford 20 high resolution runs in total. And then the question is, how do we want to divide the computational budget between high resolution and between also the machine learning runs? And that's given in this picture. So here I checked for well, 5 combinations of high resolution and machine learning runs. Which combination would give me the most accurate solution? So on the left, the 20-0 would be just 20 runs with eNKF, no machine learning runs. And on the right, I have 200 machine learning runs and 0 high resolution runs, which gave me unstable results, very high RMSE. Also, the 20 gives you somewhat high RMSE. And really the optimal here seems to be that you have to use high resolution combined with some machine learning.
Hey, Jeffrey, just a reminder that you have maybe under a minute to wrap it up. Thank you.
Okay. Yes, I have, I think, one. Yeah, I will manage. Yeah, then the final picture I want to show is then what is then the influence of this lambda parameter. So this determines how much we correct the high resolution ensemble, which is given here for 2 combinations. So I used lambda equal to 1/2 before. And you can see that in general, this lambda parameter, but 1/2 seems to be about optimal. And I still want to test this for more combinations, high and machine learning runs. Okay. So very briefly then, so what have I shown with this is that with this multi-fidelity eNKF, with the machine learning surrogate, you can reach similar accuracy with less high resolution runs. And if you have a fixed budget, then really this combination of machine learning and high resolution gives you the best performance. And for future work, I want to apply to a more realistic case, investigate maybe multi-fidelity and other data simulation algorithms, and perhaps look into methods of how you can estimate this lambda parameter. So yeah, and that was all for me. So thanks for listening.
Thank you, Jeffrey. Thank you. Great. It was a wonderful presentation with many new ideas on how to combine physical models with neural network implementations using standard eNKF approaches. I'll remind again everyone to post your questions in the YoPod. I do see already one question from Joshua, and I'll read it out. Have you considered vector-valued multi-fidelity Monte Carlo extensions, which would lead to matrix weights rather than scalar lambda? And then he points out to a recent work of that for an ensemble variational implementation.
Okay, yeah, that sounds interesting, definitely. So I will check that work out. No, yeah. So I know in the general framework you have like some optimal gain matrix with some S, which is an optimal gain matrix. But I just assume for simplicity that it's one parameter, so that you don't have to estimate this whole matrix. But that could be a nice extension, I think. Yes.
Great, and he has a link in the YoPod if you would like to check further the reference for further discussion. I would ask a question on myself. You know, I'm curious to have this benchmark and maybe to ask you whether you've tested it already. If we have this naive implementation where we forget about the multi-fidelity, but maybe we try to combine both the physical model ensemble and the machine learning ensemble and just naively apply an eNKF, What kind of degradation would we expect to see in this case? Do we see the theoretical advantages of treating the ensembles? I think it would be a useful benchmark, perhaps. Have you tested that, Jeffrey?
No, so I've mostly looked at either fully high resolution or fully machine learning, but you can of course, combine it into one ensemble. So I know like other papers where they've done that. So that could be interesting to check still. I think multi-fidelity, because you have also this lambda that you can sort of give some weights, maybe depending on how accurate your machine learning model is, that would give you an advantage than putting it in one big state vector, or like big ensemble. But I'd have to check that.
Yeah, thank you. I appreciate the answer. And this is a wrap for today. On behalf of the entire organizing committee,